Let us discuss a problem of linear programming. Let us discuss a linear programming problem solution using simplex method. So here the question is to minimize z equal to x2 minus 3x3 plus 2x5 subject to the constraints 3x2 minus x3 plus 2x5 less than or equal to 7. Then minus 2x2 plus 4x3 less than or equal to 12. Then the third constraint is minus 4x2 plus 3x3 plus 8x5 less than or equal to 10. x2, x5, x2, x3, x5 greater than or equal to 0. Now, the simplex method algorithm that we are considering is for a maximization objective function. So the first task is to convert the objective function to a maximization problem. So before starting with the standardization procedure, here we are given three variables x2, x3 and x5. So these are a set of three variables. Usually in all the problems we are coming across variables like x1, x2, x3 or y1, y2, y3 or x, y, z. So we are familiar with such a set of variables. But here just like those the variables, here we are given x2, x3, x5. That's all. So there is no specialty to this particular problem because of the presence of x2, x3, x5. These are just three variables. Okay. So let us get into standardization. So in standardization, the first thing that we have to do is to make the problem a maximization one. So we write maximize, let me put it as z dash, maximize z dash is equal to minus x2 plus 3x3 minus 2x5. So we shall add the remaining variables later. So minimization problem is converted to a maximization one by multiplying the whole right hand side by minus 1. The first constraint is a less than or equal to inequality 3x2 minus x3 plus 2x5. We have to add a slack variable since we have here a less than or equal to inequality. We add a slack variable s1 to the left hand side of this less than or equal to inequality in order to make it an equation. So similarly with the second constraint minus 2x2 plus 4x3, we add another slack variable because that is also a less than or equal to inequality and the right hand side is 12. The third constraint is minus 4x2 plus 3x3 plus 8x5. That is also a less than or equal to inequality. So we add the third slack variable in order to make that an equation. So here we write x1, x2, x3, x5, then s1, s2, s3 greater than or equal to 0. So it satisfies a non-negativity restriction, and you know that the slack variables are all assigned with cost 0 in the objective function. So we can write it as 0 s1 plus 0 s2 plus 0 s3. So you need not write it. So I have just written it here in order to show you that this slack variables are assigned with cost 0. Okay, now let us, so that is the standardization step. Now the second step is to make the function to find the initial basic feasible solution. So that's the second step. First step is the standardization. Second step is to get the initial basic feasible solution. We know that there are three equations, and there are 6 unknowns. 6 variables and 3 equations. So we set the excess number of unknowns, that is 6 minus 3 unknowns equal to 0, and we solve for the remaining set of variables. So here the variables that are set equal to 0, they are called non-basic variables. So we take from this given expressions the non-basic variables as the variables that are originally in the problem, that is x2, x3, x5. They are taken as a non-basic variables. They are assigned with value equal to 0. So when they are assigned with value equal to 0, we get s1 is equal to 7, s2 equal to 12 and s3 equal to 10, and these are called basic variables. So these are the basic variables. So this is the initial basic feasible solution. S1 equal to 7, S2 equal to 12 and S3 equal to 10 with, and all the other variables are with value equal to 0. So this gives you the initial basic feasible solution. Now let us solve the given LPP. So let us write here the basis. The initial basic variables are x3 are our S1, S2 and S3. S1, S2, S3 are the basic variables in the initial iteration, and all these S1, S2, S3 are with cost equal to 0. So let us write here the cost. So here I make the first column as corresponding to x2. I just give it as the name y1 in order to explain the algorithm in a better way. I denote this first variable by the column with the column name y1, second variable x3 with the column name y2, and third variable x5 with the column name y3. Then s1, s2, s3 are assigned with column names y4, y5 and y6. So here we can see that x2 is with cost minus 1. You can consider this cost of x2 from the maximization objective function. Then x3 is with cost 3, x5 is with cost minus 2, then s1 is with cost 0, s2 is with cost 0 and s3 with cost 0. So on the top we have written the cost associated with the basic variable. So let me write it as Cj. So these are the costs associated with the basic variables. Now let us fill in the columns. So the basic variables s1 is with value 7, s2 is with value 12 and s3 is with value equal to 10. X2 coefficients from the three equations are 3, minus 2 and minus 4. X3 variables are with cost equal to minus 1, 4. X3 variable are with coefficients equal to minus 1, 4, 3 from the three equations, and x5 variable is with cost with values equal to 2, 0, 8, and s1 coefficients are 1, 0, 0, s2 coefficients are 0, 1, 0 and s3 coefficients are 0, 0, 1. So we filled in all the values from the given standardized linear programming problem. Now let us find our get our value of the objective function z as an objective function, or z dash. Here it is z dash. So here we have the maximization of z dash. Now in order to calculate this z dash, we use a formula. Z dash is equal to cb into xb. cb into xb will give you z dash. So 0 into 7 plus 0 into 7 plus 0 into 0 into 7 plus 0 into 12 plus 0 into 10 equal to 0. Now we are going to find the net evaluations zj minus cj. Zj minus Cj is Cb, Yj minus Cj. So this is how we calculate the net evaluation Cb, Yj minus Cj. So Cb is the first column, Cb is this first column, Yj is the corresponding column for which we are going to find the net evaluations, minus Cj is the cost written on the top. So let us see the net evaluation, and the first iteration the net evaluations will be simply the negative of the cost values, because the cost of the basic variables, cost corresponding to the basic variables are all equal to 0. So the net evaluation is simply the negative of the cost values. So 2, then 0, 0, 0. So we have all the net evaluations, and there is a negative net evaluation indicates that the solution can be improved further. So the existence of a negative net evaluation indicates that the existing solution is not optimal. It can be improved further. Now, so the variable corresponding to the most negative net evaluation enters the basis. So that means x3 should enter the basis. So in place of x3, so when x3 enters a basis, number of basic variables. So here the number of basic variables is already equal to 3. So when one more variable enters the basis, the number of basic variables increases to 4. That is not possible. So we have to make one variable leave the basis. Okay. So in order to get that leaving vector, we apply the minimum ratio rule. So minimum ratio rule is obtained for finding the leaving vector. So in order to find the leaving variable, we use the minimum ratio rule. So let us calculate the minimum ratio rule. Minimum ratio rule is xbi by yij. Minimum ratio rule is we find the ratio xbi by yij provided this yij is strictly greater than 0. So xbi, this column is xbi divided by yij means the entering column value. So this is the entering column. So 7 by minus 1, that is not possible because yij should be strictly greater than 0. Then next ratio is 12 by 4. 12 by 4 equal to 3. The next ratio is 10 by 3. So we have the three ratios. 12 by first ratio is invalid, second ratio is 12 by 4 and third ratio is 10 by 3, and we know that this 12 by 4 is a minimum ratio. So correspondingly the second variable S2 leaves the basis. Okay, so we got entering column. So we got an entering column. This is the entering column. And we got a leaving vector. So this is the leaving row. This is the leaving row. Entering column and the leaving row. So the element common to entering column and leaving row, this is called the pivot element. So here P is a pivot element. 4 is a pivot element. 4 is a pivot element. Pivot element means the leading element or the most important element. So this 4 is a pivot element. So the remaining transformation to the second iteration depends upon this pivot element 4. Okay, now let us modify the basis. Let us modify the basis. Now when we modify the basis, S1 has no change because S1 has no change. S2 leaves the basis. So in place of S2, we have to write X3. So S2 leaves the basis and X3 enters. So X3 enters in place of S2. Then the third element is S3 itself. Now we can write the cost directly. Cost of S1 is 0. Cost of X3 is minus 3. Cost of X3 is 3 and cost of S3 is 0. Now remaining all values should be computed with respect to the pivot element. Okay, so now the first step is to make the pivot element equal to 1. And the idea behind making this pivot element equal to 1 is, you can notice from this first iteration, this is a first iteration. This is a first iteration. From the first iteration, you can see that the basic variables forms an identity matrix. In every iteration, the coefficients of the basic variable or the columns corresponding to the basic variable forms an identity matrix. So here you have 1 0 0 0 1 0 0 0 1. So hence this the column corresponding to the basic variable forms an identity matrix. So that is always there, and that is why, and you can also notice one more thing, the net evaluation corresponding to the basic variables are all equal to 0. So that can also be taken as a checking point in each iteration. The net evaluation corresponding to the basic variables will be equal to 0 and the basic variables forms an identity matrix of the required order. Okay, so in order to make, so when this X3 enters the basis, the column corresponding to X3 should form the middle column of the identity matrix. That means the column corresponding to X3 should be of the form 0 1 0. So in order to get the column in this particular way, we are dividing this 4 by 4 in order to get it as equal to 1. Okay. So hope you understood why we are dividing this pivot element by the same element. The idea behind is to convert it as a second column of the identity matrix. Okay, now let us do the transformations. We are dividing the pivot element. So let me write R2 is transformed as R2 by 4. We are dividing the entire row by the pivot element. So here 12 by 4 is 3. Then minus 2 by 4, it is minus 1 by 2. Then 4 by 4, 0 by 4, 0 by 4, 1 by 4 and 0 by 4. Now, so this is our R2. Now, all the transformations are done with respect to R2. So, you can see that, now please note that this is our R1, this is our R2, R3 and this is our R2. So, R1 and R3, this R1 and this R3 are going to be changed with respect to this R2. Okay, so the transformation is we have to make this minus 1 equal to 0 with reference to this 1. So we have to make the minus 1 equal to 0 with respect to this 1. So the transformation is R1 plus R2. So this is our R1 element. This is our R2 element. So minus 1 plus 1 will make it as equal to 0. So that is why we write the transformation as R1 to be transformed as R1 plus R2. So let us do the transformation throughout the row. 7 plus 3 equal to 10. Then 3 minus 1 by 2. 3 minus 1 by 2 is 5 by 2. Then minus 1 plus 1, it is equal to 0. Then 2 minus 0, it is 2 itself. Then 1 minus this 1 minus 0, this 1 plus 0, it is equal to 1. Then 0 plus 1 by 4, it is 1 by 4. Then 0 plus 0, it is 0. Okay? Okay. That's it. Now let us do the transformation. Let us do the transformation of this 3, this element 3 with reference to this element 1. So this the 3 in the third row of the first iteration should be transformed as 0 with reference to this one. So that we should write the transformation as R3. R3 means this R3 or R3 minus 3R2. So all the transformations are done with respect to the second row. Second row is our most important row. All the transformations are done with respect to the second row. So R3 minus 3R2. So let us make the operation throughout. Let us apply this elementary transformation throughout. So it is 10 minus 3 into 3. So 10 minus 3 into 3 is 10 minus 9 equal to 1. Then next element is minus 4 minus 3 into 1 by 2. Minus 4 minus 3 into minus 1 by 2. So it is minus 8 plus 3 by 2, or it is minus 5 by 2. Minus 5 by 2. Then this is 3. This element is 3 plus 3. 3 minus 3 equal to 0. This is 8 minus 3 into 0. So it is 8 itself. Then this is 0. Then this is this element is 0 minus 3 into 1 by 4. So 0 minus 3 by 4, and this is equal to 1. So we transform so we made all the transformations till the second iteration. So second iteration is partially complete. Now what remains is we have to find the value of the objective function. So Z dash is equal to, now the value of the objective function changes from 0. So 0 into 10 plus 3 into 3 plus 0 into 1. So 3 into 3 equal to 9. So that is the value of the objective function. So you can see that the value of the objective function increased from 0 to 9. Now we have to calculate the net evaluation. In order to calculate the net evaluation, we have to apply the formula CB Yj minus Cj. So this is CB, the first column is CB. Then Yj is the column for which we are going to compute the net evaluation, minus Cj. Cj is the cost written on the top. So it is 0 into 5 by 2, 0 into 5 by 2, then 3 into minus 1 by 2, then 0 into minus 5 by 2, So it is minus 3 by 2. Then there is a cost on the top, so plus 1. So it is minus 3 by 2 plus 1, it is equal to minus 1 by 2. Now the net evaluation corresponding to the second column, it is 3 into 1, 3 minus the cost written on the top, so 3 minus 3 equal to 0. So you can see that this x3 column is a basic column right now. X3 has become a basic variable, so its net evaluation is equal to 0. Now for the next column, the net evaluation is 0 into 2 plus 3 into 0 plus 0 into 8 minus 2, it is 2. Then for the next column, net evaluation is 0. For the next column, it is 3 by 4. And for the last column, the net evaluation is 0. So you can see that the net evaluation corresponding to all the basic variables are equal to 0. Okay, so right now we are in the second iteration and we got the value of the objective function and all the net evaluations. Now this here you can see that there is again a negative net evaluation. So here there is again a negative net evaluation, so that indicates that the solution can be improved still further. So we have to make the variable corresponding to this most negative net evaluation enter the basis. So this first column enters the basis, that is correspondingly x2, the first variable enters the basis. Now when this x2 enters the basis, we definitely have to find the leaving vector. In order to get the leaving vector, we are applying the minimum ratio rule. So let us calculate the minimum ratio rule. Minimum ratio rule is xbi by yij. So let us calculate xbi by yij. xbi is 10 by 5 by 2. Then next ratio cannot be taken because the denominator happens to be negative. So here we have minus 1 by 2. So the denominator cannot be negative. It should strictly be greater than 0. So the second ratio cannot be taken. Similar is the case with the third ratio. The third case also, the denominator will be minus 5 by 2 and that is not acceptable. So there is only one ratio and hence this first row, the variable corresponding to this first row leaves the basis. So this is the leaving row. This row leaves the basis. Now let us improve the solution. Let us improve the solution. That is S1 will be replaced by X2. This is the column of x2. This entering column is the column of x2. Then x3 remains in its position. S3 remains in its position. And the cost corresponding to x2, the cost, you can see that the cost corresponding to x2 is minus 1. This is the cost corresponding to x2. So let us write it here, minus 1. For x3 the cost is 3. For s3 the cost is 0. So rest all the computations are based upon the pivot element. So that means we have to multiply the first column throughout by 2 by 5. We have to divide by 5 by 2 or we have to multiply by 2 by 5. So it is 2 by 5. So hence 10 into 2 by 5, that is 4 in the first, as a first element. Then as the next element it is 1, 5 by 2 into 2 by 5. Then we have 0. Then we have 4 by 5, 2 into 2 by 5. Then 2 by 5. Then it is 1 by 4 into 2 by 5. That is 1 by 10. Then the last element is 0. So this is our R1. This is our current R1. Okay. Now we are going to do the remaining operations with respect to this R1. Okay, so let me write here. This is our from the previous iteration. This is our R2 and this is our R3, and this is our R1. So we are going to make the transformation with reference to the R1 that we have modified right now. Now we have to make the second element minus 1 by 2 equal to 0 with reference to the corresponding element in R1. So the transformation should to be applied is R2 plus 1 by 2 R1, R2 plus 1 by 2 R1. So let us do the transformation. It is 3 plus 1 by 2 into 4. So 3 plus 2 equal to 5. Then the second element is minus 1 by 2 plus 1 by 2 equal to 0. So 1 plus 0, then 0 plus 1 by 2, 0. Here we have 0 plus 1 by 2 into 4 by 5. So it is 2 by 5. So hence this element is 2 by 5. This element is 0 plus 1 by 2 into 2 by 5. So this element is equal to 1 by 5. This element becomes 1 by 5. So this element is 1 by 2. Here it is 1 by 4. 1 by 4. This element 1 by 4 plus 1 by 2 into 1 by 10. So it is 5 plus 1, 6 by 20, or it is 3 by 10. 3 by 10. So this element is 3 by 10. Then here we have 0. Then third row should be transformed as R3 plus 5 by 2 R1. R3 plus 5 by 2 R1, and when you do the transformations correspondingly, you will get the first element as equal to 11. That is 1 plus 5 by 2 into 4. It is 1 plus 10 equal to 11. This element is 0. This element becomes 0. Now the 8 gets transformed as 8 plus 5 by 2 into the corresponding element in the first row, that is 4 by 5. So 8 plus 2 is equal to 10. Then the next 0 gets transformed as 0 plus 2 by 5 into 5 by 2. 5 by 2 into corresponding element in the first row. So 8 plus 0 plus 2 by 5 into 5 by 2, it is 1. Then next one is minus 3 by 4. Minus 3 by 4 to be transformed as minus 3 by 4. So the number 8 gets transformed as 8 plus 5 by 2 into corresponding element in the first row, that is 4 by 5. So 8 plus 2 equal to 10. Second element, next element is 0, 0, this 0. This is going to be transformed as 0 plus 5 by 2 into 2 by 5. So 0 plus 1, it is equal to 1. Next element is minus 3 by 4. Minus 3 by 4 to be transformed as minus 3 by 4 plus 5 by 2 into corresponding element in the first row, that is 1 by 10. So it is minus 3 by 4 plus 1 by 2. Minus 3 by 4 plus 1 by 4. So it is minus 1 by 2. Minus 1 by 2, and the last element is 1. And now let us write the value of the objective function. It is minus 1 into 4 plus 3 into 5. So it is 15 minus 4 equal to 11. And the net evaluations are minus 1 into 1 plus 1. So the net evaluation for the first two columns are 0 and 0. The net evaluation in the next column is minus 1 into 4 by 5. So minus 4 by 5 plus 3 into 2 by 5. So 6 by 5. So it is 2 by 5, positive net evaluation. Next net evaluation is minus 1 into 2 by 5. So that is minus 2 by 5. Then plus 3 into 1 by 5, plus 3 by 5. So it is 1 by 5, again a positive net evaluation. Next net evaluation is minus 1 into 1 by 10. So that is 1 by 10. Then plus 3 into 3 by 10. So plus 9 by 10 minus 1 by 10 plus 9 by 10, it is 8 by 10. Next net evaluation is 0. And hence we got all the net evaluations as strictly as greater than or equal to 0. So the current existing solution is an optimum solution. So we conclude that we got an optimum solution. So the existing solution is an optimum solution, and let us write down the optimum solution. The maximum value of Z dash is equal to 11, but since the original problem was a minimization one, so we have to write minimum value of Z. Minimum value of Z is minus 11 with x2 is equal to 4. The value of the x2 is a basic variable for the optimal iteration. So x2 is equal to 4. x3 is also a basic variable in the optimal iteration. Hence its value is equal to the value of the x3 from the optimal table. Then x5, the third variable in the question, is not a basic variable, so it's a non-basic variable with value equal to 0. So this is a solution. Minimum Z is equal to minus 11 with x2 equal to 4, x3 equal to 5 and x5 equal to 0. Thank you.